Yeah, and before we talk about a different cluster model, different density-based cluster model for subspace clustering, it is maybe worth to mention that there are different variations of clique, meaning they have the same grid-based cluster model, but they differ a little bit in terms of different density definition. For example, some variants use the entropy of cells and subspaces rather than just simply counting the number of points in units, the density of units. Or some variations that differ in grid construction methods. For example, there is one method that uses adaptive intervals, not fixed length intervals as in clique, but adaptive intervals. In that case, in the first case, downward closure property is still implemented, so the whole thing works as we just got to know it. In the later case here with adaptive intervals, the downward closure property is not implemented anymore, so in that case we need to use best first or something like that. We talked about variants that don't use grid-based, density-based clustering methods, and we will just see one of these variants, subclue, which uses the density-based cluster model of dbScan, which is not grid-based. What is the problem of grid-based clustering model anyway? So you recall that from our survey that of course the positioning of the grid influences the clustering. So here, for example, it is sometimes very hard to find a suitable threshold tau such that the points here, the grid cells here, are all dense, but this one here is not dense, maybe because this one here is probably not a cluster, but this one here is a cluster. And of course we have to set tau for the given xi. We have to set tau to at most 4 in order to grab or to find this cluster here, because then all these 4 grid cells here are dense, they are neighboring cells, they are connected, so they are one big cluster. But then also this cluster here is reported, obviously. So there are different ways to get around that with post-processing and stuff like that, but that is always a little nasty. So the problem of grid-based clustering models is actually that the partitioning of the data space into grid cells is oriented according to the data space. So we partition the data space in order to define the volumes here. The volumes are the grid cells, and the grid cells are defined by this partitioning. And the partitioning is according to the data space and not according to the location of the points. And that is obviously different in the dbScan model. dbScan model is the maximal density connected sets, and the density now is defined with respect to the location of the points, especially the volumes are defined with respect to the location of the points, because we look for each point in the epsilon neighborhood, meaning in the range around the point with a given radius epsilon, distance threshold epsilon. So that is the epsilon neighborhood. And if there are more than tau, or in that case min PDS points in this epsilon neighborhood, then we say that this point is in the middle, in the core of a cluster, in the core of a dense area. So this point here is then a core point, called a core point. So that is the basic concept of dbScan: core points, that are points in the core of a dense area, meaning that the epsilon neighborhood of these points contain more than min PDS points. So again, we have a volume now around points with a given epsilon range, and the minimum of points that we expect in this range, in this volume. So if we have core points, well, then we know that this point here should belong or should be in the middle of a cluster, and all the points in the same volume around this point with radius epsilon should be in the same cluster, right? So we know already this sphere here, if it's a Euclidean distance, then the epsilon neighborhood, of course, is a sphere. We know that all points in this sphere here are in a dense area, so they are in a cluster. Now, a couple of those points, or all of those points, could be core points too. So since they are in the same cluster as P, all the epsilon neighbors of those core points should be in the same cluster as P. Yeah? Because as long as we follow this chain of core points, we don't go outside of a dense region. Yeah? So core points may have core points in the epsilon neighborhoods, and they may have again core points, and then core points, and their core points. So we can build this transitive chain of core points to find these density connected sets, and dbScan clusters then a maximal density connected set. Yeah? Like these maximum connected dense units here. We also look for maximal connected volumes, and the volumes are now these spheres, hyperspheres around the points, containing more than min-PDS points, of course. Yeah, so the cluster model is now a little richer, a little bit more expressive, and we can, of course, detect clusters of arbitrary shape and size, and also location, in the corresponding subspaces at least. And the naive approach, of course, would be to apply dbScan in all possible subspaces, which is obviously not a good idea, because then we need to explore an exponential number of those subspaces. So the question is, can we somehow use a branch and bound bottom-up subspace clustering search and use the clustering information from a lower dimensional subspace from a previous step in the bottom-up subspace search, in order to decide whether or not there are potential clusters in the higher dimensional subspaces, like we did with these dense grid cells. So if we know that there is no k-dimensional grid cell, any k plus one dimensional extension of this k-dimensional subspace, or of this k-dimensional cell, cannot be dense too. So the question is, does that also hold for density connected clusters? Well, there is a good and a negative point. The negative point, for density connected clusters, there is no monotonicity. But the positive point is that for density connected sets without maximality, so density connected clusters are maximal density connected sets. For maximality, it's not monotonic, but if you give up the maximality, density connected sets are actually monotonic. So we'll see that on the next slide as an example. So we can again apply these a priori style subspace search paradigms. So because we know that if a cluster C is a density connected set in subspace S, then C is a density connected set in any subspace T. And the maximality has to be given up, because C can be larger in the projection, as we will see. The other way around, if C is a cluster in S, it need not to be a cluster in T, because maximality might be violated. In T there may be additional points. That's what I just said. And a cluster in a high dimensional subspace will be a subset of a cluster in the projection. That's why maximality is not fulfilled, but density connected sets without maximality is actually monotonic, and we'll see why in this example here. So the circles here indicate the epsilon neighborhoods, and well, if P and Q are density connected, meaning that they are connected through some core points here, that's a kind of arbitrary thing here, but anyway, forget about the density threshold, especially about min-PDS. Let's just assume that we have this connection here. Then this connection, of course, if you project all the epsilon neighborhoods with the same epsilon, of course, because the epsilon is fixed, and also the min-PDS is fixed, then of course we get the same connections in all but both projections, obviously. So if P and Q are density connected via some other objects in a higher dimensional subspace, they are also in their lower dimensional projections. The other way around, if P and Q are not connected, not connected here in a one-dimensional, here in that case in a low dimensional projection, a one-dimensional projection, they cannot also be connected in a higher dimensional projection or a higher dimensional superspace of this lower dimensional projection here. Yeah? So here Q and P are not connected in B here, yeah? In this one-dimensional projection B here, so they cannot also be density connected in any higher dimensional projection containing B as one of the features. Yeah? So that is the monotonicity of density connected sets.